Okay, so this is section 5.3. We're going to talk about two big tests, the divergence test and the integral test. Let's start with a quick review of vocabulary. The nth partial sum of an infinite series is Sn, which is the sum k equals 1 to n of a sub k. We had to switch the index to k because n is being used as the ending point. So if I write out what that is, it's the sum of the first n terms, a1 plus a2 plus ... an. And closed form is writing it with a summation sign. And a series converges to a number s if the limit as n goes to infinity of the sequence Sn is equal to s. So we define the convergence of a series in terms of the convergence of a sequence. So it's a little bit confusing. So far, we have two tests. We have the geometric series test and telescoping. So today we're going to do two more. So here's a theorem. If an converges, if a series converges, the limit of the terms must go to 0. Typically, we don't use the theorem in that form. We use the contrapositive, which is the nth term for divergence. I just call it the divergence test. If the limit as n goes to infinity of an is not 0, then the series diverges. Then the sum n equals 1 to infinity of an diverges. Because if it converges, then the limit of the terms is 0. So if the limit of the terms isn't 0, the series must diverge. And there's no converse. If the limit of the terms is 0, you don't know anything about the series. It may converge, it might not. So let's apply the divergence test to three series here and see if we can get a conclusion. So the first one, our an is n squared over n squared plus n. So we have to look at the limit as n goes to infinity of that sequence. Now that's infinity over infinity, so I'm going to divide top and bottom by n squared, which is the highest power in the denominator. So we get 1 on top, 1 plus 1 over n on the bottom. Again, I divided top and bottom by n squared. And now I can take the limit, so draw the limit sign, and I get 1 over 1 plus 0, which is 1. Now 1 is not 0, so the series diverges, I'll use just big D there, by the dt, divergence test. So the divergence test is conclusive there. The terms didn't go to 0, so we can say that series diverges. Okay, let's do another one. Let's take the limit as n goes to infinity of the terms, 1/2 to the n, that's 1 over infinity, because that's the limit as n goes to infinity of 1 to the n, which is 1 over 2 to the n. 1 over infinity is 0. So divergence test is inconclusive. Inconclusive. We don't know. The divergence test doesn't tell us that this diverges. It might not. But actually, this is a geometric series, and the absolute value of r is less than 1 because r is 1/2. So we do know that series converges by the geometric series test. So converges by geometric series test. Next one, limit n goes to infinity of the nth term, 2n over n squared plus n. That's infinity over infinity. So I divide top and bottom by n squared. That's 2n over n squared would be 2 over n. N squared over n squared is 1. And n over n squared is 1 over n. Now I take the limit. 0 over 1 plus 0 is 0 over 1, which is 0. So the test is inconclusive. I don't know whether this converges or diverges. In the next section, we're going to talk about comparison tests, and we'll have a good test for that, and we will be able to determine that this actually diverges. So that's something to look forward to. Okay, so recap of what's going on, because it is very confusing. Every infinite series, which is a sum, a series is a sum, has two associated sequences A sequence is a list of numbers. So a series is A1 plus A2 plus A3, ... A sequence is A1, comma, A2, comma, A3, ... So AN is called the sequence of terms. And we looked at those sequences in the divergence test. We took the limit of the sequence of the terms. Also associated to an infinite series is SN, which is the sequence of partial sums. All right. If a series converges to a number S, then we know the limit as n goes to infinity of the terms AN is 0. Because if it weren't 0, then the series would diverge by the divergence test. If it weren't 0, the series would diverge, okay? And the limit of the partial sums is S, and that's by the definition of convergence, all right? Now, suppose AN diverges. Then, what do we know about the limit of the terms? We don't know anything, so don't know. That limit might be 0, it might be a half. I mean, we don't know anything about it. But we do know something about the limit as n goes to infinity of the partial sums. If the series diverges, this limit does not exist, or it's plus or minus infinity, which also means it doesn't exist. If this limit existed and it were a number, then the series would converge. It's a lot to wrap your head around, so take some time and think about that. All right, meanwhile, we're going to move on to the integral test. And what you do with the integral test is you have a series. Let me just jump down here. You have a series like this. You replace the series with an integral, 1 to infinity. So you replace the n with an x, you replace the summation with an integral, and you look at whether or not that integral converges or diverges. If it converges, the series converges. If it diverges, the series diverges. So that's what this says. And there are some conditions. The function f of n, which is the function you get from the terms, in this example here, it would be 1 over n. That has to be continuous, positive, and decreasing. And if that's the case, then whatever the integral does, the series does too. They converge or diverge together. Okay, so how to use the test? You define f of x by replacing n with x, and you make sure that requirements are satisfied. Usually that's just a visual check. Then you evaluate the integral. If the integral diverges, the series diverges. If the integral converges, the series converges. Okay, so let's show the harmonic series diverges with the integral test. So we've got f of x is 1 over x. That's a positive function on 1 to infinity. It's continuous and it's decreasing. So the requirements of the test are satisfied. And we have to evaluate this integral, 1 to infinity, 1 over x dx. Now that's an improper integral, so we need to replace it with the limit as k goes to infinity of the proper integral 1 to k, 1 over x dx. So remember, when we did improper integrals, leave the limit off and just evaluate the proper integral and then take the limit of your answer. So this is ln of the absolute value of x between 1 and k, which is ln of the absolute value of k, but k is positives because we're going from 1 to infinity, minus ln of 1, which is 0. So now we have to take the limit as k goes to infinity of ln k, all right? And that is infinity. So the integral diverges. Thus, I don't know why I numbered this because I stopped my numbering system, so I'll just erase this. Thus, the sum 1 over n equals 1 to infinity diverges by the integral test. I'll use IT for integral test. The integral diverged, so the series diverges. Okay, let's do another one. We're going to test this guy. So our function f of x, we're going to replace this with the limit, with the integral. In this case, we're starting at 3 to infinity. You can start at 1, 2, 3. You can start wherever you want, and the integral test is still valid. 1/9 e to the x dx. Our f of x is 1/9 e to the x. That's in the denominator. That's positive, decreasing, and continuous. So we're going to evaluate this integral and see what happens. So we're going to start with replacing this with the limit as k goes to infinity of the integral from 3 to k of 1/9. I'm going to write this as 1/9 e to the negative x dx to make the integration easier. I've got, this is f of x, 1/9 e to the x. It's the same as 1/9 times 1 e to the x, which is the same as 1/9 e to the negative x. But if I write it like this with e to the negative x, I can use my Bible formula to integrate. So now we'll drop the limit sign for now. 3 to k, 1/9 e to the negative x dx is negative 1/9 e to the negative x between 3 and k, which is negative 1/9 e to the negative k, which I'm going to write, well, I'll write it like this for now, e to the negative k minus e to the negative 3. So now I want the limit, I'm going to take the limit of my answer, limit as k goes to infinity of negative 1/9. To see this limit a little bit better, I'm going to write e to the negative k is 1/e to the k minus, and e to the negative 3 is 1/e to the 3. Now as k goes to infinity, 1/e to the k, that goes to 0 because 1/infinity is 0. So this is going to be negative 1/9 times 0 minus 1/e to the 3, which is positive 1/9e to the 3. So the integral converges to 1/9e to the 3. So the series converges also by the integral test. Not necessarily to the same number, okay? You can't say it converges to 1/9e to the 3, but you can say it converges because the integral converged. So I did an example of each one on purpose to show you that the integral test can either be used to show something diverges or converges. It all depends on what the integral does. Okay, so now here's a practice problem for you. You should pause the video and do it out. I have the answer at the end, so I'm not going to go through it on this video. And then I want to wrap it up with another test, actually, which is the p-test. And we'll use this quite a bit in the next section for very simple infinite series. They look like n goes from 1 to infinity, 1/n to the p. Those converge if and only if p is strictly greater than 1, okay? They converge if and only if, that's what double arrow means, if and only if p is greater than 1. So let's determine p in these 3 examples and decide whether the series converges or diverges. So in the first one, p is 1. So the series diverges because 1 is not bigger than 1. It has to literally be bigger than 1. And that's actually the harmonic series. Let's back it up. We showed that that diverged using the integral test, but now we have another test that tells us the same thing, and it's a lot easier, the p-test. If we had known the p-test ahead of time, we could have just said, oh, that diverges because p is 1. Next one, p is a half. So the series diverges because a half is not bigger than 1. The next one, to determine p, we're going to need to rewrite this as, let's see, n to the 7/3. So that would converge because p is 7/3, which is bigger than 1. Okay, and that is it for those 2 tests. Next section, we're going to do comparison tests, which are incredibly useful and fun.